Hi, I'm glad to present my work, Smooth Swap, a simple enhancement for face swapping with smoothness. My name is Joseph Kim, and this is joint work with Jae-hoon Lee and Byung-tak Zhang at Kakao Brain and Seoul National University. The work is about making face swapping models simpler and easier to train, focusing on the smoothness of embedding. This is a distinctive approach compared to the previous models, which often use complex model components and loss functions. Let me explain the details from the next slide. First of all, what is face swapping? Given two images A and B, or a source and a target, a face swapping model needs to synthesize the third image C, which has to have the identity of A, and except the identity, it has to be perceptually the same as B. Then, what's the main difficulty here? It is that the two conditions are in a competing situation. To consider the two conditions, two loss functions are usually employed: ID similarity loss and perceptual similarity loss. The ID loss is formulated quite straightforwardly. We use an ID embedding model to extract the ID information as vectors and compute the distance. In contrast, it's not easy to design the perceptual loss. We want to measure the difference of the ID relevant part only, but there's no good way to separate out the ID information. So we usually fall back to L2 loss or VG19 loss, which prevents any kind of change from B. Since this loss is too simple but too strong, the ID loss is often dominated by it. As a result, models change the ID only minimally. We want to prevent this, and what we need is a stable and consistent ID gradients. We want to minimize any noise in the gradient during training. To do so, the main idea is to train a new ID embedding using supervised contrastive loss. Contrastive loss is known to make the embedding space smoother, and a smoother space can give more stable gradient directions to guide the swapping model. We note that most of the previous models use arc face embedding. While arc face is a state-of-the-art face recognition model, it's optimized for the discriminative task, and thus the space can be non-smooth and it is not the best choice. Training a smooth embedding as proposed gives three advantages. We can use simpler generator architecture, simpler loss functions, and we get faster training speed. Let's compare. As depicted, previous models use complex architectures, often with handcrafted components and external modules. This requires additional loss functions and incurs difficulty in loss weight balancing. In contrast, our smooth swap model is simple. In smooth swap, we have a simple unit-based generator. There's no dedicated designs for face swapping. Just the embedding vector is added at each layer, computed from the newly trained ID embedding model. Loss functions are simple as well. The first two are the ID and the perceptual loss explained earlier. The third is an adversarial loss to make the images irrealistic, and that's it. Comparing the experimental results with other models, our model shows good generation quality. In particular, the results marked with red boxes shows active change in face shape following the round chin of the source identities. The qualitative results show the same trend. Our model is good at actively changing the identity. While it's not the best in the perceptual scores, the model marks decent numbers. Importantly, it ranks the first in the overall score. Our model also shows faster training. Compared to the same model with arc face embedding, it shows faster conversions both quantitatively and qualitatively. Finally, we tested our model on wild images, as shown here. And we also tested on oil paintings, which are never shown during training. Our model generalizes quite well in both cases. Let me summarize and conclude. We proposed Smooth Swap, a simple and fast face swapping model. The main idea was to use a smooth identity embedding suited for a generative task. Smooth Swap showed comparable or better performance with a considerably simpler architecture and loss functions. And this is expected to be especially useful for industrial applications and beneficial for tackling more complex problems. Thank you, and see you at the poster 16A, session 3.1.